Does anyone sit in front of you? Usually,
No. Usually no one sits up in the front.
I can try out my microphone. Just mixing this. You have a notebook that I can use. That you're not going to use.
No, I use my tablet typically,
Okay.
but I don't use this one as
I
much.
just need just to clip on to something. Tell people to watch out for the tripping hazard.
Yeah. I'll use this.
We just put another notebook on. Just a cover.
Actually, that's not how it works. That might make it worse. Honestly.
Stuff over. Let people know about the tripping.
I have a deck.
I got
You
it
ready?
now. Yeah.
Oh, you want to sit down here?
Oh no. I have it upgraded. It's a
Okay.
microphone. It'll
Okay, sorry.
it'll pick you. No. It's fine.
Okay.
It'll pick you up. I'll be so much better. But,
Yeah.
But like you're already good enough.
All right, thank you. We will not wait. We should have another 3 students. Just remind you, we end of last class, we discussed the dynamics or the energy, and those energy assumption is the work done by the force. So we analyzed first the total force, or the net force do the work on the single particle from 1 to 2. What we know is the total work actually equal to the difference of the kinetic energy. So that is first. Then second, for each individual force, right? So S means type of force. Then the work done by each individual force we define is this. Then here we are going to consider among this type of force, there are particular force which in any path, closed path, the work done on this the particle always equal to 0. So for this particular force, we find that is nothing but is equal to the negative of a gradient of the Vi, which is a potential energy of field. So that's be a function of R. This is also a function of R. So this is particular force, which called the conserved force, that's be field force. That's be exist in the whole space. And associated with this is nothing but there must be a potential field, and the gradient of potential field energy, that negative gradient, that is this force. I think that is end of the almost last class. Then the work done, of course, this one is 0. That means for closed path, since it's a function, therefore the difference from initial back to the origin, there's no difference, because it's a function that does not depend on path, only depend on initial position, final position. So for the closed path, the everything is equal to 0. But for finite path, let me see, conserve, due to the considered force, 1 to 2, that's be equal to, by this relation, right? Negative from 1 to 2, gradient of the potential R, dr, and we know the gradient is partial V, partial R, right? So that cancels, so that is negative 1 to 2, dVi, and this is the total differential, so that is negative final position 2 minus the initial position 1, that is the potential energy. So you can see the work done by the conservative force is nothing but it will change or decrease the potential energy, right? Because we have a negative sign here. So then you can see the total work or total by the net total force that done on system is just change the kinetic energy. Then for the conserved force, it only changes the potential energy. So we have this. Then now we are going to derive so-called the work energy theorem and what is the total energy, right? So now let us okay, just use this one. So now let's consider again this total work should be defined from 1 to 2 is net force. Okay, dot this one. Now the net force we are going to separate into the okay, let me give up. So I need to mention again here. So this is okay. Let me just come to here. So this is associated with the particular potential. We will have associated with that is conservative force. Now here we have all the type, right? Type I. So all the type. Now this I, and here in right. So that is this one. And then now we are going to classify this in terms of conservative or non-conservative. So all the type I, if it is conservative, that is the work done by the conservative force, plus from 1 to 2, all the non-conservative force, right? So we can classify the force by two, either conservative or non-conservative. Non-conservative. Okay, so the first part we are to obtain, that is nothing but this change of potential energy. So I'm going to sum all type I for this part is this negative Vi, okay, 2 minus Vi1 is here, right? For each conserved force, we have associated with each potential energy field. Then we are going to sum all type. Then the remaining part, this part, I'm going to say that is all the work done by the non-conserved force. So I'm going to use the non-conserved from 1 to 2. And we know what is this left-hand side should be T, okay, T1, T2 minus T1, right? That is the total change of total kinetic energy, or in this case, just kinetic energy with a single particle. So now we are going to move this to this, or to the left-hand side, just move this part to the same side of this. So we will have T2 minus plus summation type I Vi2 minus T1 plus summation type I Vi1. That equal to all the non-conserved force do the work. Then let's look at the left-hand side. So left-hand side here, kinetic energy to potential energy. So that is E2 total energy minus E1, right? That is change of energy, right? And this one is nothing but work energy theory in this mechanics, classical mechanics. Okay, and when, so conservation, right? So when This is the change. Now we know the change of total energy include kinetic energy plus potential energy is if there is non-conserved force do the work. So if this one equal to 0, so we can know the conserved force do the work, then we have the energy is conserved. So when the total energy conserved is if there's no the non-conserved force do the work, right? All right, so now for the single particle, we have this discussion. How about the dynamics of linear momentum? How about this dynamics of angular momentum? How about the dynamics or change of the total energy? We have this derive those formulas or give us theory. Now we go to many particle system. So for many particle systems, those for each particle will have those, but the only difference we sum of all together. So we have introduce another concept or quantity we call the center of mass. With that can help us to analyze the dynamics property of total linear momentum, total angular momentum, and total energy. So now we consider the second one, mechanics of a system of particles. When we have a particles means many particles, right? Particles. So here, suppose we have the S particle. If this is the coordinates, the orange O here, then we have Ri at the position here, the S particle with mass Mi, and we may have also the GS particle, G with mass Mg, and others. So in this case, we have many particles. Then we first introduce the center of mass. Okay, there's no comma. So center of mass. This is not classical mechanics. This is center of mass, capital R, right? The capital R is that we are going to introduce the center of mass is sum over all the product of Mi, Ri, and divided by the sum over all the total mass, right? From 1 to n, suppose we have n particles. So that is a definition, right? And by this definition, we give another vector we call the center of mass. Suppose this center of mass is here. I know there's some other, I just want to do not make a, usually it's be here, right? Some here, but since we have some other, I just assume it's here. And let me make it bigger. Okay, that's fine. So suppose it's here. Okay, then you can find we have a relative distance between the center of mass to the S particle. We call R prime I, and another one is R prime G, right? So we have a relative position respect to R. Then, okay, so now capital M is summation for all the mass. Then we have R I prime is R I minus capital R, right? You can see this relation vectors. With this introduced, then you will see there is an automatic sum by products will come. First, summation I from 1 to n M I R I prime. So we'll have by product this equal to 0. Do you agree? Or I need very simple to prove, right? So prove, because let's look this summation. M I R I prime is summation M I R I prime is here, right? Okay. R I minus capital R. Okay. Equal summation I from 1 to n M I R I minus, because capital R does not depend on this I, right? So I can take outside. And this is nothing but the capital M, total mass, right? How about this one? This one is numerator of this. So that is product. So that is capital R sum over all M I, and the second term is same. So that's why they cancel each other. M(I)0, right? That's the first one. Second one, we also have this byproduct. Immediately know the MI(RI) prime dot, that is velocity, also equal to 0. Because when you do that derivative, you can do the derivative time derivative here. Very easy, right? So let me just use another proof, right? So proof, okay, let me just this. Proof here, we do the D, this one, because mass is constant, right? So D, this answer, that is this dot, right? And this dot means, right? I just do the term D, this term dt, so that is this, only this term, and that is this two term. Then you see here, you see here, okay, this one. Then here, for this term, if you can, I take t outside, dt outside, because this does not depend on I, right? So that is I from 1 to n m(I)(RI) prime, right? R, sorry. Okay. Let me see. RI. Yeah. Okay. That is this one, and the minus here. I keep this one. Sorry, no. I keep this one. So now this one is nothing but again is this product, right?
Yeah.
So that again, then you come to here. That is this one, and 0. Do you mean? Because this one is R, capital R multiplied with summation. So that's a D capital R dt, which is R dot.
Yeah.
And this one. So we have 2. We are going to use those. Okay. So that is first introduce the concept about the center of mass. Now with this idea, we are going to discuss what is the dynamics of total linear momentum, what is dynamics of total angular momentum, what is the total energy with the total work, right? So now let's first consider dynamics of total, let me just use symbol. So let's look at this. So first we need to find the total linear momentum is sum over all the individual particle is linear momentum, right? By definition. Okay, now you can see here, this one is summation I from 1 to n m(I) dRI dt, right? And again, you will see here, you will see very easily that is summation I dt. I can make this d dt outside, so this is summation I from 1 to n m(I)(RI). Then this is nothing but this d dt capital R, right? And mass is this one. Right, that makes sense? Okay, so that is, if I'm direct, use the linear momentum of center of mass, right? That is the speed multiplied the total mass. So, what this means? The total linear momentum sum of all the particles together actually is nothing but equal to the linear momentum of center of mass. Okay. So that is the first we define what, or we find the relation, or what is the total linear momentum. The next one we are going to ask ourselves, what is dynamics, right? Now this dynamics. Here's the capital. We are going to find this, and from this we are going to find from each individual particle. We already know that, so we just use that information. Now let's first try to, since we have either for each individual particle, the force also has an external force and internal force, because here we have many particles. each particle have the external force exists on each particle and the interaction between each particle. So now we are going to classify the force in terms of total force of the system. One is, okay, let me see. Let's do this. For each individual, right? For each. So now I'm going to use the substructure I means the ice particle. If I use the superscript is a type of force. So the ice particle, the total force on ice particle, we have, now we are going to I use X means external force. So we classify in terms of this external force, ice particle, the total external force, and plus internal, right? So internal is here. The ice particle, all the G not equal to I, and then we have all the, so this one is the internal force. On ice particle. We have sum over all the neighbors, right? So that is sum over all the G if G is not equal to I. That is the net force on each ice particle. Now the total, so the total force on this total system, this n particle system, should be sum over all this net force on each individual particle, I net. And then here we have a summation for all this external force, net external force on each individual particle, plus here I from 1 to n, and then or I is not equal to G, or G is not equal to I, F I G, right? So we have these two. That is, we are going to analyze the force in terms of this external and internal in this case. Okay. Now the difficulty or some additional term come from here, right? If of a single particle, only external force, no interactions because of single particle. But if the many particle system, we have additional. So to deal with this additional interaction or the internal force, we need some of restrict us to consider the force that only follow some law. One is a weak law of action-reaction, another is strong. So now let's introduce the this so-called okay. If the Fij obey the weak law of action-reaction. So what is the weak law of action? That is Newton's third law, right? The Fij always equal to Fji but opposite direction. So that is weak law. Okay, so and most case we know that is followed, right? So if this, then we can find, okay, so now let's look at the summation, second one, right? Summation I from 1 to n, and G is not equal to I, or I is not equal to G. It's fine. G not equal to I, Fij. So now we can sum it as a pair, right? So sum over all equal to, for example, F12 plus F21. This is one pair plus F13 plus F31 and O, right? So those are pairs. This. So we are going to sum this as a pairs, and then we look each pair. You will see each pair equal to 0, right? Because this. So immediately we know sum of all the internal force for the total n particle system is to be cancelled, and that makes sense because that is only internal, right? So we have this. If we have this, now we can go answer this question. Okay, now we come to here. So therefore, let's look this. The total linear momentum, the dynamics total linear momentum is equal to the dynamics of center mass linear momentum that's equal to by let me just by definition, right? So that is b dt for all each individual linear momentum of particle, right? And this one is each individual particle is dynamics, and that by the first one we already obtained, that is nothing but the Newton's second law, that is the total force, right? So this let me use S particle, the net force, and the net force is here. There are two parts, external and internal. So now here, continue. So then I from 1 to n. This is external plus internal, right? Is this one, right? This is a total force. And this one is total force. Now this one 0, so finally we found that it's only depend on all the external force. Sum over all the individual particle is external force. Or I'm going to use the total external. So now we can see if we want to analyze the dynamics of this total linear momentum of center mass, we just look the external force. You don't need to consider the internal, right? That is the dynamics of this linear momentum. And when the linear momentum is conserved, if the total external force equal to 0, right? Immediately we have this, the total linear momentum as well as this linear momentum of a center of mass should be conserved. And that is like if your center force, right, problem only has the center force which conserve the force. So there's no, and those conserve force is an internal force. Then there's no external, but they know that the system has a conserved, constant linear momentum that is conserved. Okay. This answer the first question. Now we go to the second one. How about this dynamics of angular momentum? Dynamics of total angular momentum. Let's look at this. And first we need to know what is the total angular momentum, like the total linear momentum, right? So then we go to look this, what is the dynamics, right? So first, the total angular momentum by definition is sum of all the angular momentum of the particle, each individual particle. Okay, and each individual particle we already discussed the linear momentum as angular momentum is this cross product of the position with its linear momentum, right? That is by definition. Now the next we are going to see how to go to details. In particular, is this related to the rotation of center of mass and the relative rotation? You will see that yes. So we can separate. That's why we introduce center of mass. So looks it's very complicated, a lot of particles in different position, different angular momentum. However, if we try to classify, you will see that is very easy. So now let us turn to N. Okay, now we want to first R is Ri is Ri prime plus center of mass, right? Remember? This is R. This is Ri prime, right? And then cross with here. This one is also since this R is so we do the derivative, that is Ri prime plus this, that is center of mass plus relative, right? So I'm going to, so here center of mass is dr dt, and the velocity of relative I is dr I prime dt, right? Because here you just see this momentum. Oh, we have a mass here. Yeah. That makes sense? Okay, so now we can go. Now we have how many terms? 4 terms. This one multiply this, and this term multiply this, and this one, and this one, right? So now let's do one by one. The first term, since this center of mass does not depend on I. I need a position. Summation m1 to n, and okay, Ri prime cross product of ACN mi, right? Yes, that is one term. Let me do this way. Mi depend on I, right? So this one cross product is VCN. Right, that's first term, because this one does not depend on I, so I'll take out. Now second one, this plus summation I from 1 to n mi Ri prime cross product Vi prime. That is second term. And number 4 is the third term is summation since, okay, you will see here R and the Cm does not depend on I, so that's cross product and summation I from 1 to n mi. The last one is R, so that's sum over, I take R outside, cross product of summation I from 1 to n mi okay. Yeah, I use that's fine. Right? Now we are going to use the byproduct which we just discussed before when we introduced the center mass. How about this term? This be 0, right? You see the product of mi with Ri prime is 0. So then the first term is 0. How about second one? Second one we have to keep it. This one is also 0. So first and the last one are 0. Then we have only 2 terms. Now the 2 terms we are going to here. Now the first one, this is total mass, right? Total mass multiply this the velocity of a center mass, that is momentum, is a PC, right? So that is R cross center mass, the linear momentum. This is third term, plus I just make the position so that this one is relative. Okay, 1, 2, n. So Ri prime cross product of Pi prime, right? MIVI prime is a Pi prime. So now you see this is angular momentum that with R. So what is this rotate R is R is here, right? So that is O. This the R rotate about O, which has this the angular momentum I'm going to use. AOCM, which is if we like all the mass concentrated on this position R, then that is nothing but this this total mass which at this position make the rotation. So that is angular momentum. Angular momentum of total mass about the position O, right? Second one, I'm going to use L prime. So L prime here is sum over O, so that is the total. Okay, here I'm going to use total since this each individual is relative angular momentum of each individual particle rotate about where? About here, right? So that is total relative angular momentum about the heat of the center of mass, about the heat of. So now you will see I have a two angular momentum. One is the rotation about this, which give us LCM. Another is all the particle relative mode about this one, about this center, so that is L prime total. So you can see this is not like the total linear momentum, that the total linear momentum sum of all just nothing but is equal to the linear momentum of center of mass. But the total angular momentum, there are two parts, right? So one is all the mass concentrate at this position R, the center of mass, and then they rotate around O. Another part is all the particle rotate about the heat of R with a relative position or relative momentum, right? So this is two parts. Now, once we have this, so we are going to see the dynamics. Okay. Before we do that, remember this is the most complicated, right? So we say if you consider this dynamic linear momentum, we use apply the Wick law. Now, for this rotation, Wick law is not enough, so we are going to also introduce this if, okay, I always obey the strong. That's weak, so we need a strong law of action-reaction. What is the strong law of action-reaction? That means we have satisfied two conditions. One is it must be satisfied with Wick law. So above the Wick law, so that is Wick law, right? And also the Fij should be parallel with Rij. That is two conditions be satisfied. Then we say that is a strong, follow strong law. So that what this means here. Okay. If this is Ri, Rj, right? Rij in this part. So if the force is also follow or parallel with this direction, then we say yes, that internal force also obey the strong law of action-reaction. And most cases, like the gravitational force, like this Coulomb force, right? Those are follow this. But magnetic force does not follow, right? So be careful. So that is case. If this is satisfied, then we have a following conclusion. Then, what is the driving torque? In rotation is torque, not force, right? Or we can say implicitly is a force to cause the dynamics of the total angular momentum. So if this case, now let's look. If this, right, then let's look at the pair. So then we have the Ri cross product with F, this Ji, that means J's particle exert force on I's particle, right? And plus Rj cross product with the I's particle exert force on J's. So let's look at these two pairs. And because they follow the first one, Wick, right? And they follow the Wick law of the action-reaction, so we have Ri cross Fji minus Rj cross product Fgi, right? I just changed the index. Ij is negative Gi, right? So then you can see this is equal to the difference, right? So the difference is Ri minus Rj cross product of Gi, right? and this is RIG. So up to here, because they are parallel, either same direction or opposite direction, but they're parallel, right? So cross product will equal to 0. So what that means, if the internal force obey the strong law, this cross product of these two pairs are 0. Then we are going to analyze the dynamics of the angular momentum with this information. So, okay, let's look at the total dynamics of total angular momentum. By definition is each individual angular momentum for each individual particle, right? Sum of all this. And we know from the single particle, we already know this dynamics of each individual single particle angular momentum is controlled by the net torque, right? Okay, yeah, net torque. This net torque includes force, external force, and internal force, right? So we are going to extend details. Okay, so that is RI cross product with FI net. Then FI net, we know we classify in terms of external and internal. 1 to N RI cross this. Okay. Net external plus, right, summation J not equal to I, Fij, or Fji, the J's particle on I. So we have this. The first term, let's keep it. The first term, I from 1 to N, Ri cross with the net external force. But the second term is summation I from 1 to N R cross with J not equal to I and Ji. And this part we can separate into the pairs, right? Extend this one as always as pairs. And this one is 0, right? Because if they follow strong law of action reaction, then they only remain in the first term. The first term is nothing but that we can define as the torque, which only exerted by the net external force. So we are going to use in the torque is this term. And that is the total external torque exerted on this system. So that is the dynamics of this total angular momentum. That's only controlled by the external total torque. All the internal will not affect the change of total angular momentum, right? So we have this. Now, keep in mind, this total angular momentum have two parts. So we have to write this way. The total angular momentum includes the dynamics of angular momentum, that total mass concentrated on the central mass, plus the total relative angular momentum, that's controlled by the total external torque, or net, whatever you use, total net. So that is dynamics for this. Now we are going to discuss which case we have a conservative law or theorem about this conservation of angular momentum. If this is 0, what kind of conclusion we have? Linear momentum, 0, right? A constant, right? We already know this one gave us constant. And also that means the that's enough, I think. Yeah, I think that's enough. So that means this immediately gives us this angular momentum of the total mass centered at the center of mass and rotate about the origin end, which is capital R cross product, right? This one. So that's V constant, right? Because the P is constant. So that is only for this case. Then what that means? This term is 0, right? The relative total angular momentum dynamics of relative total is controlled by the external torque. Total external torque. That is in case if we have external force at 0. But external force 0 does not mean the external torque is 0, right? The force may be up and down cancel, but it is not the torque. So we have consider that is this one. And second, if the external torque, total external torque is 0, then we have this relative total angular momentum is constant, right? So only when, so we have two conditions for the total angular momentum conserved. First, total force be 0, external force, and second, total external torque should be also 0. Then we have the system is conserved, the total angular momentum is conserved. Okay. Good. So we have the many particle system we discussed. How about the dynamics total angular momentum, linear momentum, and dynamics total angular momentum? Now we go back to see the energy, right? Something like we consider the single particle. So number 3 is relation between total work and the total energy, right? Let's look this. And we already have the idea about this, the single particle, so we can easily analyze this by some more together. But there are one more thing is it still come from this internal force. So we need to deal with a little bit, spend additional time for that. So now let's first consider the total work. The total work done by the total force on this system include this external force and internal force, right? From 1, if the system, all the particle from 1 to 2. Okay, so that is all this, each particle has a net force and displacement. Okay, so now if I'm going to rewrite this one, since we already have a single particle, that is W I index subscript 1, 2. Do you agree? I'm going to say okay, here I dropped this superscript I because that time I consider there may be not only one force, it's a different type of force. Now here I'm going to say, maybe I'm going to use total, whatever as total. Maybe let's do this index. I total 1, 2. That makes sense? That is the total force exert on the S particle, and this total force do the work on the S particle. That is a change or total work on the S particle, right? And that is the difference of energy, kinetic energy of S particle. Okay, since we already use, we are going to use the result from, sorry, this is N. Ti2 minus Ti1, if you agree.
Hello?
Yes.
2 represents the path, I think 1 to 2.
1 to 2.
It's
Yeah,
path.
so that is the path.
Okay.
That is a path from 1 to 2. That's the S particle.
Yeah, the part.
Then this is all the force on the S particle to do the work. And that is, remember, that is a total kinetic energy change, right? So that is S. Then sum all together is very simple. Total kinetic energy change. Here, introduce total kinetic energy is sum over all the kinetic energy each particle. And here we already gave this, some, I think we have the formula, right? That makes sense? Okay. Here I didn't introduce the center of mass. This is still this absolute the velocity for each particle, not a relative. Okay, that's very simple. So now we have this total work done by this total force on all the particle. Okay, now before we go to further, I want to discuss this, determine how to determine the total kinetic energy in different way, because later when we introduce Lagrangian, we know that it's kinetic energy minus potential energy. So to deal with different type system, how to determine the total kinetic energy, that either depend on you use the absolute each individual particle the kinetic energy, or we separate into the center mass kinetic energy and the relative. Right. So now let's express. Oh, okay. Let's consider tau in in two ways, right? And which way you are going to use is depends. Which way is easier for us to use? Okay, so now let's t by definition, right? So that is I from 1 to n. Now the half of m I vi is the inner products, right? Okay, now then we are going to introduce. So that is the method 1. Okay, the first way you can obtain the kinetic energy by. Right, let me just. It's direct here. So now here, let me take half outside. Mi, Vi is, we know the Ri is Ri prime plus capital R, right? So we are going to use that way. So that is derivative, that is center of mass, the velocity plus the relative velocity, inner product of. I just rewrite. And then you can see we have 4 terms. So with these 4 terms, again, you will see the 2 terms at 0 because this by product, we know that the. So here, let me write again here, Mi, then this is a C VCM square, right? That's the first term. Second one is this one multiply this and 0, so they are the same. So twice of half of Mi, I from 1 to n and Mi, then this Vi prime inner product Vc, right? VCM. That is it. This one multiply this, or this one multiply because VCM does not depend on I, so I take outside. And the last one is this, right? So I keep here half of Mi Vi prime squared, right? Then we know this is 0, since we already discussed before this property of center of mass. So we have a 2 term. First one, I'm going to say that the first term is the kinetic energy of these all the mass are centered at the center of mass position, and plus T prime, and the T prime is we call this, let me see, kinetic energy of center mass. This one is kinetic energy of relative, or just say relative of motion about the R, right? The relative means the relative velocity is always back to the heat of R. That is relative velocity. So we have 2 terms. One is the kinetic energy, if we can determine the center of mass, so we can get this kinetic energy of center of mass, then the remaining part come from this relative kinetic energy. So that is if you say V1, the first, okay. This is the first method or formula. And the second one is the simple. So you just sum all the single particle kinetic energy. So either way, and sometimes mix together. So now let's do example, see how can we write examples. Yeah, you have question? No question? Okay. So example first one, let's look if we have the incline and we have a disk, make rotation, right? This is a disk. And we have a total mass. We have a radial A. Go down. Suppose we have the center mass velocity C. So in this case, this one is easier, right? Because if you consider each particle, this formed by the old particle, right? And with the central mass here, this is a relative position. It's too busy. I don't want, but you know that this is formed by the old particle, right? So you have, I'm going to easily to write in terms of this one, since here, center mass is simply, okay, and the relative part in this case, actually you can, you know that is rotation, right? We have angular rotation kinetic energy. The details I will not write down here. So you will see that is half of, if rotation is omega square, and moment inertia, right? So that is T1. If you know this, so I think you know how to get this rotation kinetic energy of disk, of a sphere, of the empty sphere over the solid, over the linear, right? All that the standard. So that give you, since those we know by the distribution of mass, if uniform distribute on the disk, we know this is this. And here, that is half of a total mass of A squared, if A is radial, right? So that is easily, if you use this formula, then that is complicated, right? Because this one you need to calculate each individual. And then you have to select where it is your coordinates here or there, and this each particle is velocity respect to that O is different, right? It's complicated. But if we separate it with this, then that's easier. So for this type of the problem, it is easier to write down the kinetic energy in terms of these two parts. Now how about the second one? Second one, we have one is poly, three parts, right? So one is poly here. If this is the center here, we have radial A, and we have a rope. Each end of rope we have two mass. So that is M1, M2, M3, and we have a rotation. How to deal with this? Okay, in this case, if you select center mass, these two you have to consider all together and center mass somewhere. It is complicated, right? Not easy. But I can write down here. I'm going to say T3, T1, sorry. I'm going to say the T1, T2, this, you can consider as a point, right? Because it's the same velocity. So T1, T2, you just use this formula here, right? If you know the velocity, depend on if you select this as axis, so that is only this or the vertical, right? So that's easier. Now this one, T3. T3 is the rotation of this poly. And then here, if you consider actually it's compound formed by the many particles, then to deal with this one, similar like this. So here, half of M1 V1 square plus half M2 V2 square, and plus here, okay, so here, TCM, since here, I'm going to index the the 3, system 3 plus, right? We have to consider the kinetic energy of center mass plus the relative energy, kinetic energy with respect to the center mass. Suppose if we select here, and if not select, but we know this is fixed, right? So this be 0. Okay, so in this case, I combine both. For these two, I use individual is better, but for this desk, we use this the second way, right? So then you can have keep continue plus m2 with 2 square and only 3 the relative. And relative, if this is desk, same thing like this. Right. So that is the second one. Third one, I think one more example is we have a two, like a molecule, right? We have a 2 items, so that is connect with this spring over this interaction between these two. It's like a force. So in this case, if this is M1, this is M2. Suppose here this center mass, if this depends on the mass, so this if this is center mass is this position. So which one you prefer is either, right? So in this case, I can either use T1 plus T2 because simply and depend on where you select your coordinates. That is a half of M1 V1 squared plus half of M2 V2, very simple. Or you can use T center mass plus relative. And relative actually in this case, since we have only 2 parts for relative, part 1 relative to the center mass or part 2 relative to the center mass. If the center mass keep constant, this is 0. Then just relative is this distance, right? And if not, you have consider 2. So easily. That makes sense? So when we deal with the detailed problem to find the kinetic energy, you just try to see which way you're going to select and how to get this total kinetic energy. All right, so now we have the kinetic energy. Now we also know the total force on the n-particle system work done on this will change the total kinetic energy. So now we'll work on the conserved force. We already know in the single particle there are several conserved forces. In the many particles, there are 2 parts, external force and internal. External force may be part of the external force are conservative, part of not conservative. Internal maybe, in most cases, internal is conservative, but let's consider in more general. So now we are going to consider the work done by the conservative force. Okay. So to distinguish now, let's consider the ith particle, the total force, include this external, total external, and plus the internal, right? Okay, now for the external, I'm going to separate into 2 parts. They maybe have this external force are conservative. So now I'm going to say here, I still use net, but maybe we have several. If we put the system is an electron or particle, put into the field, there's a gravitational, you have considered there's also electric, the Coulomb force. So those are all the conservative force. So I just say sum of all, right? All the possible conservative. To be, I just make count as means conservative to save the time, right? So here plus non-conservative, external, all the non-conservative. Okay. Internal also have, right? Internal, just say. Internal for each one may be either it is conservative, I use this notation, or non-conserved. Okay, so now let's consider all the conserved force do the work, and we know that's being associated with the change of the potential energy. So now how to derive those energy? Let's try to define. Let's first look this. Okay, let's look the external conserved force. Let's look this. So this one, just consider one of it, right? So then you sum all together is net. So now one of the conserved force, which is external. Then let's look this one. So the work done by this, we already know that since we define this conservative, that means we have the relation with some existing potential, right? Now I'm going to use Vi, V external, this potential is due to the external force that the external potential I's, right? So they have this relation. And from here, we have this, the work done by this external conserved force that give us this the negative change of Vi external 2 minus V external minus 1, right? So that we just use single particle discussion. Okay, then the O, right? So O, so we have all the n particle, I from 1 to n, all the work done by this external conserved force. If I use net, that means another summation, right? So now so you just keep in mind when I use this index, means we have several conserved force, external several conserved force. And each one is this, right? So sum over I from 1 to n, and then this negative Vi external. Now I'm going to use it net, means sum over all together, all this external potential force. Okay. So we introduce the total, then we have the total external force, potential for the whole system. It is sum over all I from 1 to n, each individual, if you consider net. If individual particle has several external potential, then the total external potential of the system should be sum over all. That is the external potential. Consider we all put this charged sphere or solid with a charged particle put into this the gravitational field and also this electric field or force. That you will have two types of the external potential. So for each particle we have two, right? So I use net. Okay, this fine. Now we are going to work on this internal. External, just if we know this external potential, then we know that there's external conserved force. Now we are going to come to here. Look this one. What does it look like? In particular, if we follow the strong law of action-reaction. So now, let's look at this one first. The i's part, the Ig, right? This GS particle exert on the i's particle, so that is Fgi internal. If it is conservative, then by definition it should be negative here. That is index, be careful here. I means we do the derivative with respect to Ri of the potential. This potential is Ig, right? It's a function of only the distance between two particles. Okay. If you consider this, right? So that is the definition. Now we are going to see, since we have a gradient of this, right? So we need to find this index we are going to replace by Ig. So how to do that? Let's look. Okay, maybe that. because this one we have either the x components I, j, x components plus y components j, I, y plus the z components, right? So now let's look at one of them. And if we know x, we know y, g is the same thing. So now let's look this x components by definition are conservative. Okay. And I think I just consider it's a conservative, right? So that is we just discuss conservative, right? So that is negative partial v I j partial x I, right? By definition. Then I'm going to use a chain derivative so that I can do this first partial derivative Vij with partial Rij or Rgi, whatever that Ij. Then the partial Rij, partial Xi. I do this. And Rij is square root xi minus xj square plus yi minus yj square plus zi minus aj square, right? So the partial Rij partial xi is just this term, right? And the half of 2 cancel, so that is xi minus xj over Rij, that is xij or Rij. So here, that's equal to negative partial Vij partial Rij and xij Rij. This is x components. The y component, z component are same. So you will see the grading of this potential, which give us the internal considered force is like this. So the total, the considered force of Gi conserved is here is minus partial Vij partial Rij, right? Those are the only difference here, right? And then it's xij I yij j plus zij k and 1 over Rij. And this is nothing but partial Vij partial Rij Rij unit vector of Rij. Or you just do the derivative of the Vij with respect to Rij and the directions along the Rij, right? That is the, you see here from here now at the notation, I'm going to give a notation is, now this is Ij. That's good, based on variables. So you see here, so they are equivalent. With this, then we can go further to find the potential energy associated with the internal, conserve the internal force. So then we have this, right? So now you can see here, because the, let's say if this Fij followed, obey this weak law, weak law of action, reaction, what happened? We know that the force Ij is negative Fji, right? So that means gradient of Ij, Vij is negative gradient of Vji, gradient of Ji and Ij, Ji, Ij, that's the same, right? Because potential is a scalar. But the gradient, this index, change index, you have a negative sign, right? Okay, now the next one, we have a strong, I think, for okay.
Prof,
Yes.
We have 3
Yeah.
minutes left.
Oh, only 3 minutes?
Yeah.
why is it called weak law of action here and strong in the previous case? Like
This one?
the name, why is it called?
Ah, okay. The weak law, right? So
Yeah, and
if,
somewhere else you had written strong law of action.
yes, weak law is only this one, right? Strong law means in addition to this, Rij is parallel to Fij, Oj. So this we are going to use, but you say we have 3 minutes. I think we can I use 2 minutes? We almost done, right? So here, I think we will have this. The pair. Now let's look at the pair. So now, look at pairs, each pair, right? So each pair we have this F, because we need to find this, the work done, this conserve, plus F DI plus Fij, consider the force on the GS particle, right? Look at this one. And now each one we have this is a negative, so you will have a negative gradient of Ji Vij Dri minus gradient of delta Ij Vij Drj. Then they are just, you see, I have so I change, so that is have a negative sign. This we take out as a negative. I'm going to take negative of V delta Ji V, whatever Ij or Ji is fine. The inside is Dri minus Drj, right? This became positive because here, this relation here. If I change index, right? So this is Ij, and now I change Ji. So this is nothing but Drij. So now we have this Ji Vij Drij. Okay, let me. I think we have the potential that is correspond to this one. So let's continue on Tuesday. Then we almost done on this many particle system. So we go to the constraint, which we are going to introduce the Lagrange. So you will see the dynamics of Newtonian equation looks very simple, seems easy, but when you deal with each force, you will see it is not easy. Some force is very complicated, which you cannot express or no knowledge about this force. So how can you work on this numerically or mathematically? So we have to consider those forces that are constrained, how to deal with constraint. Okay, all right. Can I erase?
Yeah.
No, it's okay. Filming is too fast, man. She's so high,
I didn't finish that. I want to watch that.
That's we didn't
noted from the to be noted from the video.
Currently, he's thinking that we know that this part. That's why she's too fast.
Yes, yes, it's too fast, too fast.
She's in the flow.
I wrote 10 pages, like I never wrote. Means
The writing is not problem. As in actually, it's
Jacob,
sometimes
you can call here. No, it's
Yeah,
not
I'm
a-
trying
Yeah,
to find
it's-
his number right now.
you can stop.
I can call.
No, no.
Or you know how to stop?
Yeah.
Yeah, go ahead.
You've had her before, yeah?
No.
I think he's coming.
You. Could you tell me when class is over? And
Yeah,
if I'm not back, you think you could take everything to the GTA office?
This one?
Yeah, just everything.
I don't know how to take it.
We have to go to VAB, right?
Yeah, yeah. So
For
really, you just
Kathy?
come over here, press
Or this
just
one?